Hey Raiders, we're going to talk about Chapter 1, Plate Tectonics, Section 4, Seafloor Spreading. Here we go. At the mid-ocean ridge, this is basically the main piece that you have to understand about seafloor spreading. This is where molten material rises up out of the seafloor, and this is what actually holds and creates a seam like along the ocean floor. Kind of like a baseball has seams that bind the leather together. This is what the mid-ocean ridge does, and it's basically what consists of underwater mountains. Now this map here, it shows the mid-ocean ridges. These red lines, these are showing you the top ridges of the mid-ocean ridge, and you can see the elevation changing and how the ocean floor, the ages of it. So the closer you are to it, the newer it is. The further away, so this greenish color here is telling you it's about 140 to 180 million years ago that was created. Ocean floor is only about, new ocean floor, it takes about 200 million years to get entirely new ocean floor. Henry Hess is the guy that studied mid-ocean ridges, and he's the one that actually supported and found the evidence to support Wegener's theory. He proposed the idea that seafloor spreading continually adds new material to the ocean floor. How does it do that, you ask? Well, what happens at this mid-ocean ridge, magma rises up from the lithospheric plate, and it pushes the continental crust to the side. So the old stuff gets moved over as this new material comes in. So it ends up moving the ocean floor like a conveyor belt, carrying continents along with them because they're connected to those lithospheric plates. Along the ridge, the molten material that forms beneath the surface rises and erupts. At the same time, the older rock is what moves outward on the sides of the ridge. As molten material cools, it forms a strip of rock at the center of the ridge. So let's look at this. So here we have our asthenospheric plate, mantle, and this is where our magma is coming up. It's going to push the material this way, and it's going to push the material this way. What happens is you have this subducting slab of rock that is actually going to fall back down in this asthenosphere, and we're going to talk about that in a minute. Okay, so as this molten material continues to rise, we're pushing that ocean floor in opposite directions, creating more space for us. So what evidence does he have? There's three types of evidence has to use to support his theory: eruption of molten material, magnetic stripes in the rock of the ocean floor, and the ages of rocks themselves. Those are the three pieces of evidence we're going to discuss. So let's look at the first one, evidence for molten material. Scientists dived to the ocean floor in what is known as Alvin. Alvin was a very, very small submarine. It fit two guys, and it was built to withstand crushing pressure from the ocean for about 4 kilometers. And this hasn't been done since then. I think there was one other time where they had done a deep dive like this involving actual humans. So what these two scientists found out was at the bottom of the ocean floor there was these pillowy like rocks which only form when molten material is quickly cooled after it erupts. The rocks then show that the molten material is erupted again and again along the ridge. So he's got this evidence from the molten material. Next piece is the magnetic stripes. These magnetic stripes have reversed themselves many times during Earth's history. Section 1, what is known as the North Pole now becomes our South Pole. This has occurred multiple times. What evidence do we have? Well, we have the evidence from the iron filings. As the molten material rises, it contains iron. That iron makes up our rocks. And as it cools, the iron filings themselves are going to align themselves to the North Pole and South Pole, that magnetic attraction. What happens is as it cools, they get stuck in place, kind of like freezing something in a cube of ice. So these strips hold actual records of the reversals of the magnetic field. Rock contains iron, okay, which has that molten material. This locked in iron bits of pieces gives it the ocean floor this striping look, kind of like a zebra. So here's what it kind of looks like. What scientists have developed a diagram to show you what it looks like. So you can see that in one direction the iron filings have this magnetic look that goes this way and vice versa. So it looks like a stripes. That's what it looks like. I don't know how to explain it any other way than that. The Glommer Challenger is a drilling ship that also gathered samples of rock from the ocean floor. To put it simply, it's like taking the Empire State Building and trying to put a tiny little pole on the end of it and to dig with the Empire State Building. It was pretty impossible to do, but they managed to do it by pumping these rocks up through these long pipe up to the ship. So what happens is these samples of rock actually gave evidence that the rocks further away from the ocean ridge were actually way older than the ones closer to it. The youngest rocks in the samples were always found in the center of the ridge. So these drilling samples also proves evidence. So what happens when all this material is being added? What's going to happen to the ocean floor? Does it keep getting wider and wider and wider? No. What happens is there's going to be subduction. This is when the ocean floor continues to get wider. Instead, the ocean floor plunges deep into the underwater canyons called deep ocean trenches. So these trenches is actually where the seafloor sinks back down into the mantle, gets melted, and becomes molten material again. In a deep ocean trench, oceanic crust is going to bend downwards. The denser material is what's going to sink back down. When molten material first erupts, it's actually it's less dense than the rock there. As it cools, it becomes denser, so it becomes heavier, and it's what's going to sink back down. So here's what it kind of looks like. So here we have our seafloor spreading, molten materials rising, seafloor is getting pushed, it's getting pushed. Here's our trench. At our trench is when two crust pieces meet. Continental crust or oceanic crust. You can have continental and continental meet, oceanic and oceanic, or oceanic and continental. But what's going to happen is the heavier, denser crust is going to sink. So here the subduction zone is going to pull this mantle back down into Earth's mantle, and it's going to melt. So this process by which the ocean floor sinks beneath the deep ocean trench back into the mantle is known as subduction. As subduction occurs, the crust closer to a mid-ocean ridge moves away from the ridge and towards a deep ocean trench. Seafloor spreading and subduction go together, okay? They work together. That's what moves that conveyor belt. Gravity comes into play here. This is a force that's going to bring the crust back down into the trench. The process of subduction and seafloor spreading can actually change the shape of the oceans. So what's kind of crazy is even though this process is occurring, sometimes the deep ocean trench sucks down more continental crust or more oceanic crust than it should, and the ridge can't create enough rock in time to replace it. So what is actually kind of occurring, what scientists are finding, is the Pacific Ocean is shrinking, and as the Pacific Ocean is shrinking, it's pulling all those continents that direction. So what in theory they're saying is the United States is actually moving further away from Europe, and so the distance in flight to get to Europe actually takes a little bit longer every single year because they're slowly moving away from each other. So that means the Atlantic Ocean is increasing in size. So as this crust is being recreated, it doesn't always get created as fast as the stuff that gets sucked back down. It is a cycle. It will come back, but it doesn't mean that it's not changing the size of our ocean floor. If you have any questions, please come see me, and I'll see you later.